Let's look at the relationship between the circular and hyperbolic trig functions. They can all be derived from Euler's formula, which is really just this, but then you can make an alternate form if you just put in negative x, which doesn't change cosine because it's even, but sine of negative x just becomes negative sine of x. And so we have these two different versions of essentially the same thing, but a cool thing that we can do is we can easily derive the complex definitions of cosine and sine just by adding and subtracting these from or with each other. So if we add, then we just get e to the ix plus e to the negative ix. So basically, it's the same thing there. And then you get two cosines, and these disappear. So you get this, and then you multiply both sides by 1/2, and you basically get the complex definition of cosine. And then when you subtract, you're just going to get this. So basically, when you subtract, you're going to have e to the ix minus e to the negative ix, and then that's going to give you 2i cosines. You divide both sides. You divide that both sides by 2i, and you get this. So this has a 2i, and this has a 2. Okay, so these are the complex definitions of cosine and sine. Well, then we can go a step further, and if you want to get the definitions of hyperbolic cosine and hyperbolic sine, just take these and put ix instead of just x. Just put an ix in the input, and then keeping in mind that I squared is -1 because I is just by definition, it's the square root of -1. Okay, and then so this here, for instance, that would be, you would get a negative x, so that would be this. And then here you'd get negative x, which would be positive. I've just switched them because normally we like to write the positive one first. And this is the definition of hyperbolic cosine, otherwise known as cosh. So people will tend to say cosh x instead of hyperbolic cosine of x because it's such a long thing to say. If you do the same thing here with sine, well, then the same thing happens, and so you go from this to this. And then one other thing we do, because we don't want that we don't want it down here, because the cool thing about cosh and sinh, so these cosh and sinh, hyperbolic cosine, people call it sinh. Okay, the cool thing about them is that they're totally real. And so to make that happen, we want to get this I out of here as well as, it goes away up here. And so what we do is we just take these two things, which is this, multiply both sides by -I, and it gets rid of the I. And here we go. So that's so here we have the complex definitions of cosine and sine, and then we have the definitions of hyperbolic cosine and hyperbolic sine, but of course these are real. One thing definitely worth noting is that cosine of ix is equal to cosh of just x, and -I sine of ix is equal to sinh of x. Another thing, cosh plus sinh equals e to the x. You can verify that for yourself here. Okay, now I want to look at, again, in the vein of similarities, or the relationship between these guys and these guys. Okay, the circular and hyperbolic trig functions is, if we look at this area, something interesting happens. You may not have thought about it before because we don't really think about it much with the unit circle. So this is a unit circle, a distance of 1. This is a unit hyperbola, and this is a distance of 1. And let's look at these two yellow areas. Now, normally we're used to thinking of this as an angle. We may use theta, but either way, this is an angle. That's the input to cosine and sine. But let's think about what's the area. I want you to see that the area is half the input. It's going to be half the angle that you put in. And the way you verify that is, well, the area would just be, so if that's x, then it would be that angle over 2 pi. You would take that ratio of the entire area of the circle, and you will get x over 2. And then I want us to see that the same thing happens over here, strangely enough, that this area, so you can make an area from the origin to some random point on the hyperbola, and then if you just figure out this area, then it's actually going to be half the input as well. I'm going to prove that later. We're going to have to do an integral, but not yet. And keep in mind, we don't normally look at this angle. That's just we don't care about that. The input to cosh and sinh is not an angle. It's just a number. Sometimes people, come up with, I think they'll call this, hyperbolic, the hyperbolic angle or something. I think I don't, but I think it's just to make people feel better. But it really, we don't use angles. These are angles. These are not. It's as simple as that. Okay. So what else? So we'll prove this area later. It's a lot harder than just getting this. We should look at, do cosh and sinh fit the hyperbolic criterion in the first place? I mean, we're calling them that. So up here, we called them that, but do they really belong? So really what we should do is take them and plug into the hyperbolic equation and see if it equals 1. And so that's what I'm doing here. So basically, if you just take, cosh and sinh and plug them into here, so we have, cosh squared minus sinh squared. These are just what we derived above. And we're going to see that sure enough, we do get 1. So this here, the way you can do it is just think of, this is really just a difference of squares. And so if you just use the idea that x squared minus y squared factors into x plus y times x minus y, and if you think of this as x and this as y, then it's not too hard to do this. And so basically you would get this and this, and now you're just adding a couple of fractions and getting this, adding these, or subtracting one from the other here and getting this. The 2's cancel. You just get e to the x times e to the minus x. By exponent properties, you get e to the x minus x, which is e to the 0, which is 1. And sure enough, these guys do belong in the hyperbolic equation. They are hyperbolic by nature. Okay. Last thing we want to do is prove this area. We want to show that the yellow area, okay, we want to show that the area in yellow is half of x. And so the way we're going to do that is, first we're going to take the area of this entire right triangle, and then we're going to subtract area B. So why are we doing that? Well, it's a lot easier than trying to take an integral with A. Just do the entire right triangle and then take the integral of B, which is slightly easier. So that's going to be the strategy. So the entire right triangle, which would be 1/2 base times height. Keeping in mind, this is the distance cosh of x, and this is sinh of x. So base times height. So triangle minus, and then we're going to figure out this orange area with this integral. That's going to be the area from 1. Okay, so this is 1 right here, to cosh of x of the integral that we get if we take the hyperbolic equation and we solve it for y, and we get y equals this, and that is what we're going to integrate here. So here's that integral, and here it is done. I'm not going to do it in this video because it's quite a horrific integral to take, and it'll muck up the video. I want to have a better flow, but I will put in the description a link to a video where I actually do this integral if you're interested in that. And so what do we got here? So basically the integral gives us all of this stuff, and then we have to plug in, we're going to do all this evaluated at cosh minus everything evaluated at 1. But the cool thing is, if you plug in 1, so you'll notice that turns into a 0, that turns into a 0, natural log of 1 is 0, so this entire thing just goes away. So we don't even have to worry about evaluating at 1 and subtracting. All we have to do is plug in cosh. So that's it. So just basically plug cosh into all of this, and when you do that, you're going to get, well, here's an x, so that's going to be cosh. And then keep in mind, so what are we going to do with this? Well, if you just look at this that we already saw is true, and you solve for sinh, well, that's going to be the same thing here. So if I put cosh in here, it's going to be cosh squared minus 1, which is just sinh, and that's what we have here. And then this, of course, is going to be cosh again, and this is going to be sinh again. Okay, so we're almost there. Now the triangle area, this is the triangle, and then we're subtracting the orange B area that's this that we just computed from the integral. And notice the triangle area and the first part of what we got from the integral is the same, so these are just going to go away. So we really just have this left. It's being subtracted, so it's going to be positive, and so we've got it down to here. And now just remember, cosh plus sinh equals e to the x. So we have 1/2 natural log of e to the x, and well, natural log of e to the x is just x. So there we go. We have proven that the areas do the same thing, that this area is half of the inputs, just like this area is half the inputs. So I think that's really cool.